Hello and welcome back. In this video I want to talk about the buoyant force, which is an upward force that is exerted on an object that is either partially or completely submerged in a fluid. And this principle that is behind this is sometimes referred to as Archimedes' principle. And this comes from this famous legend that a Greek king who had had a crown made and suspected that maybe the crown was made out of a metal that was other than gold, asked Archimedes to determine whether or not the crown was made out of pure gold, but without melting down and destroying the crown. And so the legend goes that Archimedes went to take a bath, and he filled the bath up to the brim, and then when he stepped into the bath, he displaced the water, causing it to spill over. And when this happened, he realized that he could use this phenomenon to measure the volume of an irregularly shaped object, like a crown. And then he ran out into the streets naked, yelling, "Eureka!" However, this legend is, of course, not true, and it doesn't really give Archimedes full credit for what he had discovered. So what Archimedes actually did was he had used the effect of buoyancy to determine whether or not the crown was real. And the way he did this was he created a scale, and he put at one end of the scale the crown, and then at the opposite end of the scale he put a block of gold, which weighed the exact same amount as the crown. And then Archimedes took this entire scale and he submerged it in water. And so the idea was that by submerging this in water, the water would exert a buoyant force on these two objects. And if the crown was in fact not made out of pure gold, then the buoyant force that was exerted on the crown would be different than the buoyant force exerted on the block of gold. And so as a result, the crown would start to go upwards as the block fell, because gold is a very dense metal, so if you mix gold with other metals, the crown will become less dense, and as a result, there will be a larger buoyant force on the crown. So how exactly do we calculate this buoyant force that is exerted on an object that is submerged in a fluid? Well, the basic idea behind this is that because pressure increases with depth, when an object is submerged in a fluid, the pressure at the bottom of the object will be greater than the pressure at the top, and as a result, the force that is exerted by the pressure on the bottom of the object will be greater than the force that is exerted by the pressure on the top. And the difference between these two forces is equal to the buoyant force. So the buoyant force is equal to the force that is exerted on the bottom of the object minus the force that is exerted on the top of the object. And this is equal to the pressure on the bottom of the object times the area of the container on the bottom minus the pressure at the top of the object times the area of the object on the top. In other words, this is just equal to the pressure at the bottom of the object minus the pressure at the top of the object times the area. And we know the difference in the pressure between the bottom and the top is equal to rho GH. So this is rho GH times area. And finally, if we think about this, if this object has a top that has some area A and it has a height h, then the height of the object times the area is equal to the volume of this object. So this is just equal to rho g times the volume of the object that is submerged in the fluid. And it's very important to remember that when we're using this formula, the rho, the mass density that we use in this formula, is the mass density of the fluid that the object is submerged in. So what happens if the object is only partially submerged in the fluid? Well, in that case, it turns out that the buoyant force is going to be just equal to rho g times the volume of the object that's submerged in the liquid. So you just use only the volume that's actually submerged in the liquid if the object is only partially submerged. So let's go ahead and look at a couple of examples. This first example says, when a solid object is completely submerged in ethanol, it has an apparent weight of 15.2 newtons. And when the object is completely submerged in water, it has an apparent weight of 13.7 newtons. The question asks us to determine the volume of the object. So remember that apparent weight, we've talked about this before, that's the normal force that is exerted upward on the object. So what we have is we have an object, and it's placed inside a container of water, or ethanol. So here we've got this container, and the object's sitting at the bottom of it. And so there's going to be this normal force that is exerted upwards on the bottom. But we also have a buoyant force that is going to be exerted upwards caused by the object being submerged in a fluid. And the sum of these two forces has to equal the gravitational force that's pulling down on the object. So the idea is that the difference in these two apparent weights will be related to the difference in the buoyant force that is exerted on the object when it's in ethanol and when it's in water. and so we can use this to determine the volume of the object. So I think I'm going to need a little bit of space here, so let me go ahead and open up OneNote. So I've gone ahead and I've drawn another picture of this object. And again, remember the basic idea behind this is that because the object is at rest at the bottom of a container, the net force that is pushing up on the object is equal to the net force pushing down on the object. So this means the buoyant force that's pulling up on the object plus the normal force that is pushing up on the object is equal to the weight of the object. So we have that the force due to gravity is equal to the buoyant force plus the normal force that is exerted on the bottom of the object. In other words, the buoyant force is equal to the weight of the object minus the normal force that is exerted on the bottom of the object. So, since we're interested in finding the volume of the object, we can relate the buoyant force to the volume of the object. So we have that the buoyant force is equal to the density of the fluid times g times the volume of the object, and this is equal to the weight of the object minus the normal force. Now the idea behind this is that this equation that I've written right here is always true. This is true for both the ethanol and the water, so I can apply it to the ethanol and water separately, and it'll give me two different equations. And I need two different equations to solve this problem because I have two unknowns. I don't know the weight of the object, and I also don't know its volume. So if I apply this to the ethanol, we have the density of the ethanol times g times the volume of the object is equal to the weight of the object minus the normal force that is exerted on the object when it's in the ethanol. And if I apply this for when the object is in the water, we have the density of the water times g times the volume of the object is equal to the weight of the object minus the normal force that is exerted on the object when it's in water. And at this point, I could go ahead and I could solve for the force due to gravity in one of these equations and then plug it into the other equation. But if all I'm interested in doing is eliminating the force due to gravity, I could also just take the difference in these two formulas. So if I do that, then over here I'll have the difference in the densities of the ethanol and the densities of water times g times volume. And I can write it like this because g and volume, that's common to these two factors. On the right side, the weight of the object cancels, and we'll have the normal force that is exerted when the object is in the water minus the normal force that is exerted when the object is in the ethanol. So solving for the volume of the object, we see the volume of the object is equal to the difference in the normal force that is exerted on the bottom of the container when the object is in water minus the normal force that is exerted by the bottom of the container when the object is in the ethanol, divided by g times the difference in the two densities. So it's the density of ethanol minus the density of water. And if we plug all these numbers into a calculator, we'll see that this volume is equal to 7.85 times 10 to the minus 4 cubic meters. So this is how we solve that problem. Let's go ahead and look at another example. So this next example asks us to determine the fraction of an iceberg that is below water given that the density of water is 10 to the third kilograms per cubic meter and the density of ice is 917 kilograms per cubic meter. So the basic idea behind this is that when you have an object that is floating in water, there are two forces that are being exerted on the object. There is the weight of the object, which is pulling down on it, and then there's the buoyant force caused by the water. And when the object is just floating there, these two forces cancel. So we have the buoyant force that is pushing up on the object is equal to the weight of the object. Now remember that the buoyant force that is exerted on an object that is partially submerged in the liquid is equal to the density of the water times g times the volume of the object that is submerged in the water. So that's just this part of the object. It's just the part that's submerged in the water. And this has to equal the weight of the object, which is m times g. Now since what I'm interested in doing is finding the ratio of the volume that's submerged in the water over the total volume of the object, I want to find a way to relate the total mass of the iceberg to the total volume of the iceberg. And the way I can do this is by using mass density. So we know that the mass density of the iceberg is equal to the mass of the iceberg divided by the volume of the iceberg. So using this, I can plug that into this equation here. So I have the mass density of water times g times the volume of the object that's submerged is equal to, well, the mass of the iceberg is equal to the density of ice times the total volume of the iceberg. So the weight is that times g. So by setting these things equal to each other, g's cancel. I'm trying to solve for the volume of the object that's submerged divided by the total volume. So if I divide, let's see, so volume submerged divided by the total volume, the way I get this is by dividing both sides by the volume of the iceberg and dividing both sides by the density of water. So if I do that, I have that the volume of the object that is submerged divided by the total volume of the iceberg is equal to the density of ice divided by the density of water. And this is going to be equal to 0.917. So this means that approximately 92% of the iceberg is below water when the iceberg's floating in water.